Good morning, friends. Today we are going to be talking about decision trees and risk evaluation. If you recall, in the last lecture we had talked about the financial appraisal of capital investments, but there we had seen that we had assumed that the cash flows involved were known with certainty, which is not necessarily true in practice. And therefore today we are going to be working with an example of a situation when cash flows are not known with certainty, and we'll see how we would like to evaluate such situations and talk about evaluation of risk in capital investments. Basically, all business decisions involve risk, and you must therefore understand what is risk and how to measure it. A risky situation is a situation where you don't know what will happen. So uncertainty is an essential component of risk, and once you don't know what's going to happen, therefore either you know that different things can happen, and therefore you might not you might not get what you expected in life. That actually defines a risky situation. We'll formally define risk for the example that we will consider, so that you can get an idea of how risk can be evaluated in real life situations. What we will do is we will talk about a device known as decision trees to represent real life investment, real life returns and risk. And then we will take an example of a product launch situation to illustrate the use of decision trees. We are talking about the product launch situation because this is the first stage in the life cycle of a production system, and we are interested in finding out which product to launch, and the environment is generally risky. So we are addressing that particular situation, and then in considering this situation we will talk about determination of optimal strategies as to how do we determine what is best to do in a risky situation. Let us present a situation, and the situation is a company is thinking of launching a new consumer product that has been developed by the company, and preliminary marketing potential has been estimated as a chance of 0.4 for a successful launch, which would result in an annual profit with the present worth of 2 million rupees. And the failure of the product would mean a loss of 3 lakh rupees. That is the situation that we are considering. Notice here that to some extent the company has an idea of this chance of 0.4, which is estimated as the probability of a successful launch for the new product. And if the product is successfully launched, it is expected that it would yield a profit, and the net present value of that profit is expected to be 2 million rupees. If the product is a failure, it would mean a loss of 3 lakh of rupees, because if the product is a failure, what it means is that all the expenses that have gone into promotion, prototype development have actually been incurred, and therefore there is a loss to the extent of 3 lakhs of rupees. And if it was doing well, then it would be able to gain 2 million rupees. So these are some figures here, and the chance of the successful launch has been estimated by the marketing department, which is actually familiar with the state of the market, the types of customers and so on. So, this is an estimate, it is a Bayesian estimate rather than a classical estimate of probability. So, what the company wants to do essentially is to either drop the idea totally, that is one thing it can do, status quo, do not do anything. So, you can either drop the idea completely, or the company can decide to take the plunge and launch the product straight away. Or if it is a little more cautious, it might want to try a test market, which can be done at a certain cost. The estimated cost here is 40,000 rupees before deciding to drop or launch the product. And the test market would obviously give us greater information about the likely success or failure of the product. And you can categorize the outputs of the test market into the following three categories, that is A, B and C, we can say. So, when you are talking about A, this is a situation where less than 10% of the public try the product. So, this is like a poor response. So, the response A would be the poor response to the test market. We may then have a situation where B, we have more than 10% of the population tries the product, but less than 25% of those who try the product buy it on a second or a subsequent equation. So, this is like a medium popularity of the product. And the third case, C, would be more than 10% of the people try the product and the repeat purchase rate is more than 25%. You see, the true success of a product depends upon its repeat purchase. You might go to the market and buy a product just because a beautiful young lady is presenting it to you, right? Yes. However, the real success of that particular product would be determined if you go ahead and buy it the second time after the first exposure. So, that is exactly what we are trying to capture here in responses B and C. Okay. So, if the repeat purchase rate is less than 25%, we classify it as B, and if it is more than 25%, we classify it as C. So, A, B and C become statistical means to classify the response of the product in terms of its popularity at the test market. So, we can sort of summarize the response of the marketing experts or the marketing department in terms of the following probability table, the joint probability table. For instance, what you see here is these are joint probabilities. So, the joint probability of success and poor response is 0.05. The joint probability of success and medium response is 0.10, and the joint probability of success and good response is 0.25. Incidentally, if you take the summation of this row, it leads to 0.4. So, 0.4 is the unconditional probability of success, and these are the joint probabilities of S union A, S union B and S union C in mathematical terms. Obviously, you would expect that these probabilities, which are only estimates, they would be, if the test market outcome says poor, you would expect the success rate to be small. So, this probability will be smaller, this should be relatively bigger, and this should be the biggest in this particular row. So, there is a logical way to estimate these probabilities, and you can therefore look at it this way. Similarly, the probabilities of failure, the highest probability of failure should be for a product which has a poor response in the test market, which is 0.45 here, the joint probability here, and we would expect these probabilities to decline. That means the failure probability is assumed to be 0 if the product has done very well in the test market C, right. This is very much like trying to say that if a candidate has done very well he is likely to get a job with 100% probability. That's what we're trying to say here, right? In something like this. Now, using this probability information and the information pertaining to the economics of the problem, let's see what we can do about this. So, the task at hand for the company is to use a decision tree to determine what is best for the company to do, and also obtain the probability distribution of outcomes for each choice and comment on the risk in each case or in each choice. That's exactly what we're trying to do through this case study. Many of you may be familiar with the notion of a decision tree, but for this particular example, our decision tree would look something like this. Let us first comment on the structure of this tree. Notice, for instance, that we start here from a circular node which we call node 1. Okay? And basically there are three options available to us. We can either decide to drop the idea, or we can decide to do a direct launch, or we can decide to do a test market. So, there are three possible routes from 1, and we go here. If you come to node 2, we have used a square node rather than a circular node. The square node specifies that this is a chance node, and anything can happen here. In fact, there are two things which can happen here. The product can be either a success or a failure, and this is a probabilistic phenomenon in this case. Okay. Similarly, if you do a test market, the results of the test market can be poor, medium, or good, the way we just described them. And when you come to these nodes, the circular nodes are referred to as decision nodes. That's the place where the decision maker can decide which road he is going to take. Whereas if you come to a square node, you don't know whether you will be thrown here or here. It depends upon the operation of a roulette wheel, which determines whether you go to success or failure according to a probability distribution. Okay. So, when you come here, if your test market response is A, then you can decide to either drop the product or launch the product. So, this is a decision node, and I can decide to do this or this depending upon whatever I want. However, if I decide to launch the product here, you encounter a chance node here, and so you might land in either success or failure of the respective of the product. Similarly, here in each of these cases you can either decide to drop or launch, and there would be success or failure. If you launch, drop, launch, and success and failure, and so on. So, this is the structure of the tree. The only thing is that we would have to superimpose on the tree two kinds of information. That is, if you drop the idea, what's going to happen? What are the consequences? You get nothing, 0 here. What would happen if it is a success? You gain 2 million. If it's a failure, you lose 3 lakhs of rupees. So, you put that figure here. So, that would be the monetary information that would have to be entered everywhere on the tree. And the next thing that would have to be done is to put down the probability estimates at all the probabilistic nodes, so that you can evaluate the tree. Now, you can do this thing. We can number the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. This numbering is essential in the sense that we will have to evaluate each of these nodes. So, as we go along, we will see how the individual node numbers individual nodes can be evaluated. Incidentally, this is the optimal decision tree. Let me explain this, and I will explain the calculations a little later, because this is the final result, and because students are generally anxious to know the final result without knowing what the intermediate calculations are. So, I thought it would be a good idea to just talk about the optimal solution before I go into the computations. The optimal solution really shows is the one which is shown in dark lines here. This solution shows that it's best for the company to do the test market and not do the drop or the direct launch. And once the test market is done, anything can happen. It can be either poor, medium or good response. So if it is a poor response, best is to drop the product. If it's a medium response, best is to launch the product. If it's a good response, it's best to launch the product. So really speaking, the three major decisions which follow node 3 are DLL, drop, launch, launch. So we have actually defined a decision strategy. So you must understand the difference between a decision and a decision strategy. A decision strategy here defines for us the entire sequence of decisions that we would be taking under all possible circumstances. Okay, we do the test market, it says the test market can land you here or here or here, we don't know where, and then from here, if you land up here, it's best to drop. If you land up here, it's best to launch. This statement is a decision strategy. Decision strategy is the sequence of decisions for all possible outcomes, and once the decision maker knows the optimal strategy, I mean, he is now equipped with all the information and he knows what to do under all circumstances. So our objective is primarily to determine this decision strategy from the information about the decision tree that we just talked about. How this is done is you first of all manipulate your probability data. We have had this information about joint probabilities of S and A, S and B, S and C, which I showed you in the previous table, and you have the information about joint probabilities of failure and A, joint probabilities of failure and B, and so on. So this was the second row of the probability table. The interesting thing, of course, is that probability of success is nothing but the sum of all these. So this figure we know comes out to be 0.4. Here in fact we are using what is known in probability and statistics as the theorem of total probability. Okay. Similarly, the probability of failure is given as the summation of the second row, which is 0.6, which is what we knew, right. Similarly, the probability of A, that is the probability of the test market outcome being poor, is the summation of these two probabilities, and this figure is 0.5. And similarly, probability of B will be 0.10 plus 0.15, which is 0.25, and probability of C is also 0.25, which is the summation of these. Obviously this adds up to 1 and this also adds up to 1, as it should. Okay. So we have actually determined the probabilities of success and failure and the probabilities of A, B and C. What it simply means is that if you look at the decision tree, what we have got here is the probability of success is 0.4 here and the probability of failure is 0.6 here. And similarly, we have been able to estimate these probabilities of A, B and C as 0.25, 0.25 and 0.5 respectively, which is what we have obtained here. So from the probability data for this case, we impose the information pertaining to the annual profits. The annual profit P is 2 into 10 to power 6, that is 2 million rupees. The loss due to a failure is 3 into 10 raised to power 5, that is 3 lakhs of rupees. And what we are saying is that the test market costs 40,000 rupees to organize. So this is the cost involved in conducting the test market. So if the product is launched straight away, what happens? Then you can calculate the value of node 2. What is node 2? Look at this example here. So what we are interested in is the profit of 2 million multiplied with the probability of 0.4 plus the loss. So, it will be minus 300,000 multiplied with the probability of failure, right. That will be the expected value for node 2. So, this value, which is the expected value for node 2, is therefore 0.4 into 2 million plus 0.6 into minus 300,000, because this is a loss, and the expected value for node 2 is 620,000 rupees. So, it is one way we have computed the value for node 2. We will adopt a similar procedure to compute the values for nodes 3 to 9 for this particular problem. Take the situation if the test market of the product is done, then what will happen? At node 9, the value, what is node 9? Let us recall node 9. It is, for instance, this particular node here we are talking about. We are calculating from the back. So, what is going to happen is the conditional probability of success here multiplied with, the total monetary value or the return here, which is 2 million rupees, multiplied with the corresponding probability of success, the conditional probability of success. Here we are going to use conditional probability of success, because this is the probability that you are on this branch. So, this is nothing but the probability of success given C has happened, right. So, similarly, the probability of failure given C has happened, this will be the probability here. So, if you compute these figures, you get the expected value for node 9 as 2 million rupees, and similar figures for node 8 are 620,000 rupees by a similar logic, and for node 7 the value turns out to be negative, it is minus 70,000 rupees. So, when we are computing from the back nodes 7, 8 and 9, we find that the expected values for nodes 8 and 9 are positive, but for node 7 it is negative. So, you can make a conclusion here, and the conclusion is that since the nodal value of node 7 is negative, indicating loss, thereby it is better to drop the product at node 4, but launch the product at nodes 5 and 6, since nodal values of 8 and 9 are positive, indicating profit. I hope this is understood. What we have simply said is the following: the value at node 7 is negative and this drop is 0. So, here you have a choice at node 4. A rational decision maker would choose 0 as something better than minus 70,000. So, he would rather prefer this road rather than going here. So, if you happen to be at node 4, the optimal decision for you should be to drop the product rather than launch the product. However, if you happen to be here, it is better to launch the product and launch the product, because the values for these two are coming out to be positive. That is the logic for this.
So, over here, sir, you have applied that conditional probability element, that PA.
Yes.
0.5, you have applied it only to one term.
No,
okay.
For instance, if you consider node 7, at node 7 we would say that this is, if you look at node 7, what is node 7? Node 7 is here, right. So, here you would have conditional probability of success here and the conditional probability of failure, right. What are these conditional probabilities of success and failure? This is SA divided by probability A, FA divided by probability A. So, this is the conditional probability of success when divided by PA of success given A has happened, conditional probability of failure given A has happened. So, that is what it is, and that is these two probabilities, which are nothing but 0.05 divided by 0.5 and 0.45 divided by 0.5, okay, and they are multiplied with the corresponding values that you have for various this particular profit and loss here, profit and failure here. So, 2 million rupees and 300,000 rupees, which is the loss, and so you get the expected value for node 7 is minus 70,000. exactly similar logic is followed for the other nodes 8 and 9. Okay. So we have these values with us, expected values, and then we've got this information pertaining to values which have now been computed for all the nodes. We start from the back, that is, we computed these values from 7, 8, 9, and then we go back, and from these values we can then compute the values for node 6, node 5 and node 4. What do we mean here? Look at the tree again. So if you want to compute the value for node 4, what you should do is compare the outcome here, which is 0, with a negative outcome here. So the value for this node will be the maximum of these values, so the value for node 4 is 0 in that sense. We are assuming that you are a rational decision maker and you will therefore not be suicidal in making these decisions. Okay. Similarly here, drop is 0 and launch was positive. So whatever the positive value was, that would be the value for node 5. Similarly, when you look at this particular situation, this is 0. When you drop, you don't get any profit, and when you launch the product, you will get certain expected value which we computed for node 9. So that would be the value for node 6. So that's precisely what we are saying here. So the value for node 6 is just the value for node 9, which is 2 million. The value for node 5 is nothing but the value for node 8, which is 620,000, and the value for node 4 is 0, because this is the better thing to do, and therefore we can directly find out the values, the corresponding values for this was node 4, and now you can find it out for node 3. Node 3, if you recall in the tree, is this particular node. So since we have computed the values of nodes 4, 5 and 6, multiply them with the respective probabilities here, and you get the value for node 3, because this is a probabilistic node. So at this node we have probability multiplied with the values for these individual nodes, and the value that we get is 655,000 rupees. This is the process of computation. Now if you summarize the results so far, what have we concluded? We have actually been able to determine in the decision tree, these are the three basic options that you have. We have been able to determine the value for node 3. We can similarly determine the value for node 2. This will be 2 million into probability of success, which is 0.4, and minus 300,000 into probability, which is 0.6, and so that will be the expected value for node 2. So you can get node 3, node 2, and also from this particular branch. So the conclusions here are that if the company drops the idea, then the expected return is rupees 0, which is obvious. I decide to do nothing, I say status quo, and I don't introduce anything, so this is not a risky thing, because I get 0 for sure. Okay, so it's a fairly certain thing. If the company directly launches the product, then the expected return is likely to be 620,000 rupees. And if the company tests the product's potential by a market survey, then the expected return is likely to be 655,000, which was the value, and minus 40,000, which is the cost of the test market. This cost of the test market that you have here, the moment you decide to do the test market, you have to pay 40,000 rupees. So this is like the toll tax that you pay for crossing a road, right? The tax on the Noida bridge. It's exactly in the same manner. No matter what the outcome is of the test market, you have to pay that amount. So that's why this is subtracted here, and you get an expected value of 615,000 rupees. So essentially what we have done so far is we have been able to evaluate the expected outcomes from these three possible courses of action: either drop the idea or launch the product, or maybe do a test market. What you will find here is that there isn't much difference between this and this. This is 620,000 expected value, and this is 615,000 expected value. And since there isn't much of a difference, I mean, at a first go you might be tempted to opt for this one because this is the largest out of the expected values of the three, and you might say that the direct launch is the most profitable option. But this option is a very risky option. This option is much less risky, and we will now do the investigation of the risk to find out exactly as to what we should be doing in a situation of this nature. Of course, our basic idea is to get some return. The company should not drop the idea. This is obvious, because if you drop the idea you don't get anything. So both the other options lead to some earnings. Instead, it should go for test market, since expected return in direct launch and test market is near about the same, but the chance of failure in the test market, this in fact quantifies risk. In the direct launch, the chance for failure is 0.6, while in the test market this chance is only 0.15 in the test market. This speaks a lot about how risky these individual proposals are. What you find here is that if you launch the product straight away, the chances of losing are 60%. So that's a risky situation, very risky situation. Now at this stage we can define risk. What is risk? Because we said one of our objectives in this lecture was to define risk and understand how to measure it. We can define risk as the probability of a negative payoff. Right? The chance that you lose some money is a good measure of risk. Chances of losing some money are, that's what your risk is, right? For instance, if you play in a lottery situation, I spend 10 rupees and I can either get nothing or I can win, let us say, a Maruti car worth 3 lakhs of rupees. Okay, but the chances of winning would be 0.00001. Okay, and the chances therefore of losing would be 0.9999. So this is a very risky venture in that sense. If it's a big draw, the chances of losing money are very high. It's a risky proposition, but it also depends upon the quantum of the loss. In a simple lottery situation, you wouldn't mind losing 10 rupees because you can afford to lose it. You will throw it away anyway, you know, buying Coca-Cola or something. Or if you don't buy Coca-Cola these days, you might want something else. So because of these kinds of situations, what may happen is that, so risk is the probability of a negative payoff. The next thing is whether the company is willing to take that risk. Are you willing to lose that much money? So if you are able to take that much risk, after all, companies have to take risk to make money. It's an important thing, okay? But this kind of a quantification is possible. So in this case, the risk associated with the direct launch is 60%, and the risk associated with the test market, we will see how this is calculated, is only 0.15. I think an interesting point that can be discussed at this stage is, I indicated to you that it is not really appropriate to talk about expected values in the evaluation of various risky options. Why do you think this is so? You see, if we say, for instance, take the example of the risky situation we were talking about, right? 10 rupees, you get a ticket for a car, and you get a car for 3 lakhs of rupees with a very low probability, and for a very high probability is that you will lose your 10 rupees, whatever it is, right. Now, if you calculate the expected value of this game, what will happen? 10 rupees into 0.99999, which is the probability of losing that, plus the probability of 3 lakhs, but probability of actually getting that money is 0.00001, something like this, right. And therefore, you would get an expected value which will be close to 10, very close to 10, isn't it? Or let us say it will be between 10 and 3 lakhs technically. So, depending upon the values of profit and loss, the probabilities, you can manipulate these values whatever they are. Now, the issue here is that that expected value has no meaning for you, because under no circumstance will you get that expected value of money. You will either lose 10 rupees or gain 3 million rupees or 3 lakh rupees for the car. You will never get that expected value. You will get the expected value only if this experiment is repeated indefinite number of times. If it was a situation which was repetitive, then expected value has a meaning. If you are doing this experiment only once, you will never get the expected value, and therefore, expected values are very misleading for situations which are not repetitive. So, that is exactly what I meant by saying that the probabilities that we are dealing with are actually Bayesian probabilities and not classical probabilities. So, when you are dealing with Bayesian probabilities, you should at best treat them like estimates of experts, and the expected value analysis that we have done actually has no meaning. So, what is the right thing to do under such a situation? So, we will for this example, we will see that we can do the evaluation of the optimal strategy by constructing the entire probability distribution of outcomes. If you know the probability distribution of outcomes for a strategy, that would give the manager enough information of what all can be done and with what probability, and he just uses that information for purposes of taking the decision. Okay? So, this is what it is. So, we talk about enumeration of all strategies, and in this case our basic strategies are these three: drop or status quo, which is one of the options, or direct launch, which is another option, or do a test market. Okay. So, in this case, let us see what are all the possible strategies. In this case, the two strategies are directly, of course, drop and launch. Apart from this, there is the option of doing a test market, and in the test market you can easily see that we can enumerate at most 8 possibilities, because in under each of these cases A, B and C for the test market, you can decide to either drop or launch the product. Okay, 2 decisions. So, 2 raised to power 3 is 8 strategies, and these 8 strategies are listed here. The first strategy could be drop, 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 irrespective of the outcome of the test market, which is like dropping the product altogether. Then it could be drop, drop, launch, DLL, and so on. So, what we will do is we will try to investigate the nature of these strategies in terms of their probability distributions, and then make some comments on what the company should be doing. So, we can talk about the first strategy, which is drop or status quo, which is very simple, and that has a probability of success and failure. There is nothing like that. So, it is just 0 expected return in this particular case. And in the direct launch, of course, what we are doing here is that there is a probability of 0.4 of success and a probability of 0.6 of failure, and that is what it is in terms of this particular strategy, these two strategies. Then take the test market strategies. So when you look at the test market strategies, for instance, if you take the drop situation scenario, that means you do a test market but decide in advance that no matter what the consequence of the test market is, we are not going to launch the product. In fact, it's pointless to do a test market in such a situation if you are going with such a bias, isn't it? But let's take this strategy, and obviously for this particular strategy the probability of success would be 0, probability of failure would be 0 with probability, and what you are losing in this particular situation will be the amount of money that you spend on the test market, which is 40,000 rupees, and that probability is 1. So you are about to lose this money without gaining anything else. Similarly, if you look at the other strategy, DDL, that is drop and launch situation, then in this case what are the consequences? The consequences are that there is a probability of 0.5 of not gaining anything, there is a probability of 0.25 of not gaining anything, and there is a probability of 0.25 of gaining 2 million rupees in this particular stage, and of course in all these cases there is a loss of 40,000 rupees, which is the cost of conducting the test market here. So what we are basically trying to do here is to determine actually the probability distributions of all these strategies and also the expected values, which we will use for purposes of guidance rather than for decision making. Something similar can be done for this third strategy, which is DLL, that is drop, launch, launch. So if you drop, launch, launch, what does it mean? It means again essentially that you will have, this can happen with a probability of 50% that you will not gain any money. There is a probability of 25 that you will gain this 0.62, and you have a probability of 0.25 that you will gain 2 million rupees, and of course there is a loss of the test market which has to be accounted for. So you can find out in this case again the probability of success happens to be 0.35, the probability of failure happens to be 0.15, and 0 probability, that is neither gaining nor losing any money, is 0.5 for this particular strategy. We would do this exercise for all the possible strategies that we have. For instance, let us take the strategy D, L and D, what it means, and let me explain to you how we got this figure. If you drop the idea, if the test market outcome is A, if you launch if it is B, and if you drop when it is C, then obviously the chances of A happening or poor is 0.5, and you are dropping it, so you get 0. And then if you have this particular option here of taking the launch strategy, then the expected value would be 0.62, that is the expected value of the launch in so many millions of rupees. And of course you would have the probability for this would be 0.25, and the probability for the third option, you know, we have 3 probabilities, 0.5, 0.25 and 0.25 in this particular situation, and so you have it here. So you have these probabilities of success 0.10, probabilities of failure 0.15, probabilities here which is 0.75.
So, but how do we do the trade-off between the expected returns and the probability of failure? Because suppose the expected returns are very close to each other, then we compare the probability of failures.
We are here not talking about the comparison, right, at the moment. We are only doing the computations, and when we do the computations, when we compile the computations, then you can be guided by both the expected value and the risk computations when you do this. We will do that when we come to this. Okay. We are at the moment merely compiling the figures for all the 8 strategies that we have. Like if it's all launch strategy, what does it mean? That in this particular situation your expected value would be something like this, 0.58 into 10 to the power 6, and the probability of a success is 0.4 and probability of a failure is 0.6. So it's equivalent to a direct launch situation without the test market. So that's what it works out to. I mean, you have this value, this value, this value. So you have a probability of success of 0.4, probability of failure of 0.6, and little loss in revenue is there because of the cost of the test market.
So what is the last term P0 equal to 0?
P0 means there could be a success, there could be a failure, and if you don't do anything, then you will not get anything. So the probability of 0 is 0 in that sense. Look at the sixth strategy. It's launch, launch and drop. Obviously this is going to be a suicidal strategy, isn't it? What does it mean? It means that if the test market says poor, you launch it. If the test market says medium, you launch it. If the test market says good, you drop it. So you are deliberately dropping something which the test market anyway. Okay, so look at this. So you find for this particular strategy, the expected value works out to only 0.08 into 10 to power 6. And the probabilities of success, failure and 0, these values are 0.15, 0.6 and 0.25. That's what it is, right? But these are now calculations are very similar to what we have done for the other cases. Let's now see what would happen here. Look at this strategy. Again it says this is a worse strategy, right? If the test market outcome says poor, you have heard of the story of a man who always used to do something opposite to what his friend told him. So it's like saying when the test market outcome is poor, he says I'll launch, and when it is medium or good, he says I'll drop. So if you do this, this is a strategy, one of the strategies. The net expected value comes out to minus 0.075. This is what you expect into 10 raised to power 6. And the probability of success is only 5%. The probability of failure is 0.45. And the probability of getting nothing, neither success or failure, is to the tune of 0.5. So success and failure here refer to primarily the getting a profit or getting a loss, and 0 is there because you might decide to withdraw and get neither a profit nor a loss, right? That's, if you remember what we said in the optimal strategy earlier, that if you were at node 4, you would rather drop the idea rather than go ahead with the launch. So you would have got 0 returns. So we are that's the 0. Take the LDL possibility again. This is 0.425 and the corresponding probabilities are shown here. Okay. Why I am showing you this is the manner in which the various probabilities can be computed, right? Now this information that we have calculated can be plotted on a graph, and it will look like this. If you look at the first strategy, which is drop or status quo, it's very simple. You will not gain 2 million rupees, you will not lose 0.3 million rupees, you will get 0 with 100% probability. So this is a purely riskless situation in that sense of the term. Okay, so we see the probability distributions of all the 8 strategies. What we find is for strategy 2, which was a direct launch, it's a risky strategy because the probability of a negative payoff is 0.6. The sum of all the probability spikes on this side will give you 0.6 in this particular case. So that's the risk, and the expected value is 0.62. So this shows that although we'll never get this money, we'll either get this much or lose this much. That's what it is showing. Strategy 3, which was DDD, again is dropping everything, but there is a cost here. So the expected value was 0.04. The test market DDL, which we considered, because we have now enumerated all the strategies, right? So, here what is happening is that this is 0. So, the risk in this case is 0. There is a 75% chance that you will get 0 and 25% chance that you will get 2 million rupees. Okay. So, in that sense the risk is only 0.25 for this strategy. The test market DLL strategy, again the risk is 0.15 because there is a probability spike here. These were the 3 probabilities that were computed. For the test market strategy DLLD, the cost again the risk is only 15%. For the test market strategy LLL, that is if you launch it, again this is equivalent to a risk of 60%. So, for all these things, the 6th strategy was a very risky strategy, 60% chance of losing the money. If you, obviously it was suicidal, you were launching when the product was no good. The strategy of launch and drop here, the risk here is 0.45. This is the probability distribution of outcomes. For the last strategy, we have the probability distribution of outcomes LDL and the probability distribution of outcomes. Now, the probability distribution of outcomes itself gives very valuable information about the strategy to the decision maker, because it tells you what you can get and with what probability. And this itself is very more useful than the expected value, because the expected value does not tell anything. So, let us look at a summary of all the strategies. We have computed these 10 strategies which are listed here: drop, launch and drop, and all these individual strategies. So, we have the profit here and the loss here, and this is the probability, right? This can happen with probability of 0.4, this can happen with probability 0.6. So, you have these figures. This is what can happen. The expectation of each strategy is calculated here, and we have also compiled the risk values for each strategy. Obviously, the least risky strategies are these 2 strategies, the do nothing strategies, 0 risk. If you don't do anything, there won't be any. If you don't venture out of your house, you are sure not to be hit by a car. So, it's the least risky strategy. That's the kind of risk associated with these 2 strategies. And then subsequently, we have, this is the strategy which is most risky, 0.75, is 75% chances of losing some money. This was when we went against the voice of the experts, that is the marketing experts. Otherwise, these are 2 strategies which have the least risk, 0.15 and 0.15. Now, if you compare these 2 strategies, obviously this is much higher on the expected value rather than this one. So, we would tend to prefer this one, but here again you can see what the gain and loss is. So, you find that in the optimal strategy, and the optimal strategy in this case works out to be this one, that is the one we showed you right in the beginning. It has a very little risk and it has a profit of 2 million rupees with a chance of 0.35, and it has a loss of 0.3 with a probability of 0.15. So, there is some risk involved there, but it is much lower than the risk, let us say, of the direct launch, which was 60% here. So, this is a systematic strategy that you can adopt for purposes of evaluation of risk. The basic idea here is to determine the probability distribution of outcomes for the strategy. So, we did it for all possible strategies. You need not do it for all possible strategies. You could determine this for only the most promising strategy. Okay.
So, for the second strategy, if the risk had been, instead of 0.6, had it been 0.2,
yeah,
then which one would we have to choose?
Now, if it would have been, for instance, 0.2, then obviously, again depending upon these values, this would have become quite attractive in that sense, right? So, the idea is really that you are minimizing the risk, but at the same time you would like to have a high expected value, though of course expected value is something fictitious, but it just tells you that how your distribution is placed, and that is why we talk about the entire distribution.
So what I want to ask is, like for the second strategy, the expected return is greater than the fifth strategy.
Okay.
And now if we keep on reducing the risk of the second strategy, then at what value that second strategy will become more attractive than the
It's
fifth?
not like that. It's like saying it's making a choice. You know, when you want to get married, you look for a girl who's beautiful and intelligent. And when you are looking for this kind of a combination, when you compare two options, you might get a. It's like saying these are like very much like those two objectives. You will rarely find a beautiful and an intelligent girl. You would find that either the intelligence level is high or the beauty level is high in that sense. So you would, in the same situation here, if you look at this example, this has a very high risk, but it's based on the expected value. It has the highest expected value. But we lower the expected value slightly and we lower the risk considerably. So you have to compromise on something. Similarly in choice for a partner in marriage, you would probably look for compromises. You would probably not get a beauty queen, and therefore you would like to sacrifice on one objective to get the other. Something similar happens here, right? It's a choice, it's a trade-off between the various things. So let us conclude. By and large, in this lecture, we have tried to define risk as the probability of a negative payoff. That's one thing. And business situations abound in capital inflows and risky revenue realizations. So the kind of methodology that has been proposed here using decision trees can be applicable to those risky business situations. And decision trees capture such situations with a finite number of decision alternatives. That's another thing. And in this lecture, we took the example of a product launch to assess the optimal strategy. I think we'll conclude here. Thank you.